Good evening, everyone. Thank you very much for joining us this evening for our next public lecture here at the Geological Society. My name is Natasha Stephen, and I'm the Director of Science and Engagement here at the Society, supported by my colleagues in the science and the events team. It's my pleasure to introduce you to our speaker this evening, but before I do, there's just a little bit of housekeeping for both those of you in the room and those of you who are watching online at home. If you're here in person today and you hear an alarm, please do treat it as a real event. We're not expecting any kind of fire alarm, so please leave by any one of the marked exits. That's one at the front here and 3 at the back. You can follow a member of staff. We're all wearing our yellow lanyards and the muster point is just outside. And we'll just check everybody is safe and has exited the building together. For those of you joining us remotely, throughout this lecture, your microphone and your cameras will be switched off, but you will be able to see and hear our speaker, of course. If you've got any questions online, please just drop them into the Q&A box that you'll see on the panel in front of you or in the chat box as well, and we'll come to them all at the end. There'll be a 15-minute session at the end for Q&A. So for those of you in the room, please put your hand up and we'll get a microphone to you. That's just so that the online audience, which I believe is around about 150 people, will be able to hear you. And for those of you online, your questions will be read out by a member of the team in the room so that those in the room can also hear the question as well before we let them be answered. Finally, this video will be live streamed onto YouTube and it will also be made available as a recording afterwards. So if you do miss anything, you can always catch up on demand at your leisure later on. So now on to our speaker, Dr. Brian Burnham. So Brian tells me that he is a geoscientist curious about the crossover between earth sciences and technology. He did his undergraduate and his master's at the University of Texas in Dallas, where he worked with geoscientists and digital artists to analyze and visualize 3D photorealistic models of 3D outcrop, geological outcrop data, something that members of our team are very good at as well here. After his master's, he came across the pond and did a PhD at the University of Manchester and then moved on to the University of Aberdeen as a research fellow, but now as a recovering academic is employed with VR Geosciences Limited, is that right? Perfect. And that's what he's going to be talking to us about today, using virtual geoscience as geology's vision quest. So without any further ado, I'm going to hand over to Brian. Thank you very much.
Right. Good evening, everyone. My name is Brian Burnham. I'm a senior geoscientist at VR Geoscience Limited, where we work on kind of the digital front of interpreting, analyzing, and visualizing digital outcrop data. So the talk is Geology's Vision Quest, and I'll be going over a bit of a brief history of 3D outcrop models, where we came from, and where we are now, some of the methods and common practices that we have and that we use to build 3D outcrop data. And you'll see the transition in technology, which allows us to build much better models these days. Go through some applications of the models, a bit from my PhD, that's what I'll be presenting on. And then importantly, I'm going to talk about conservation and accessibility and what 3D outcrops it gives us on that front. And then I'll briefly touch on what I'm calling new virtual frontiers, which you can probably guess what that will be. So I hit next. Right, so I should probably first define what a 3D digital outcrop model is. Quite simply, it is a three-dimensional representation of an outcrop. These can be in the form of photorealistic models like the one that you see here, where we take a bunch of photographs and then we build a 3D representation of this outcrop. We can have other attributes to it as well. I won't discuss all the other attributes that you could apply to this, but you can imagine things like the roughness of this outcrop as things come in and out of the outcrop. These are the sort of attributes that we can apply to it. But most commonly, they tend to be these photorealistic versions of the outcrop. So we're trying to represent what we would see in the field, but something that we can visualize on our screens at home. So now that we know what a digital outcrop model is, I thought I would just briefly talk about my personal history with 3D outcrops. So as you can see in the bottom right image, I first went on some field work in about early 2007. And this was, I was a field assistant, but really I was a glorified pack mule because I carried lots of heavy batteries and I carried a tripod with me up and down the hills in the Guadalupe Mountains. It was quite a slog to go up and down the hills carrying 22, 25 kilos of kit. But when I saw what we could do with the data, that was it. I was hooked. I was like, we can build 3D representations of what I'm looking at standing on a hillside. So the model that you see up in the top left, that is the first 3D outcrop model that I built. And this is a model, a static image of the video that you just saw, where this section is a place that I visited as an undergraduate student. I was taken there to look at some effluvial sediments, and I thought this would be a great area to collect because I want to come back here again. I may not be able to drive because it was a 5-hour drive from where we were. So I couldn't go there again easily. So I thought if I build a 3D model, I can take it back and then I can look at it again. So throughout my academic career, both at UT Dallas, Manchester, and then finally at Aberdeen, I've worked in various companies along the way. And I think this is really important to mention because it allowed me to view creating and analyzing 3D outcrops from a practical perspective. How can I take this outcrop data and how can I use it in other applications, whether it be subsurface geoscience or environmental geoscience? What can I do with the data other than making a nice, pretty picture? Well, an outcrop geologist, these are the common tools of the trade. As you might expect, we've got a notebook, compass clinometer, hand lens, maybe GPS if you're modern, and then usually a topographic map so we can mark down where we've been. And we usually produce something like this, which is a 2D representation of the thing that we mapped. So we've got the different colors, which might be the different rock types or the different facies. We mark on there, say, faults that we've mapped in the field. So we can use these tools and we can make these maps, which are nice and they look really pretty. But it's something that is quite old. So William Smith, if you're not aware, he published the first map of the stratigraphy in England, Wales, and the southern bit of Scotland. And what's amazing about this is this completely revolutionized the way that we think about rocks in the subsurface. No longer do you just walk along a pebble and you see a cliff section. You can think about the rocks underneath your feet. So everything that's we can't see, that if we map it like this, we can start to relate it spatially and importantly, temporally. Well, we still do that today. It hasn't changed. I've taken students in the field and I've given them a compass clinometer, a notebook, and I said, go forth and map, do things, take pictures, take measurements. And then they produce maps, just like I showed you previously. And it's an important and critical skill to teach students how to map rocks and how to try to understand things in 3 dimensions. But it has its limitation because it's a piece of paper. It's not digital. It's not recorded. We can't transfer that knowledge. But in the 1990s, the late 90s, we saw like a shift in this idea. GPS, the Global Positioning System, was unlocked in the late 90s. And then also around the year 2000, selective availability was turned off, which means the GPS on your phone and the GPS that you might take out in the field, we now have access to it. What did that do? That allowed us to map spatially things like geological boundaries. So no longer was it just a map in between some contour lines, the boundary was in 3D space, which is a huge leap forward. But perhaps a more fundamental shift happened in the early 2000s. So the late Carlos Aiken, who is imaged on the right there, he's using what's called the laser rangefinder. And if you don't know what that is simply a laser gun where you pull the trigger and it fires a laser at an object and the object comes back to you, and you record the distance from the laser to the point. And so you can create something like the point cloud, which is what we call a 3D representation of an object by points in the bottom left there. And this is just to show that if we map a corridor or a hallway, we can generate a three-dimensional representation of that. But what was fundamental about this is it allowed us to map features at a great distance away from where you were. So we use the GPS that had been unlocked for us, and we can get our position where the laser rangefinder is, and then we can fire the laser at an outcrop. So for example, this image here is the Ferron Sandstone, and we've got some fluvial successions in there. And they use the laser rangefinder to map all of the bounding surfaces within this outcrop. So all of the colored points there, those are the different surfaces in that outcrop. It's very difficult to measure those surfaces in length and vertically. Many geologists will abseil down a cliff, but I don't know most that do. If they can map it digitally from a distance, they will. It's safer. And we record the data in 3 dimensions. We have that data point. So this allows us to not only map surfaces along, say, a 2D outcrop section, we can start to map canyons. So the image in the left is a canyon system. And I don't know for those at home, you may not be able to see it, but the canyon snakes from the bottom of the screen to the top of the screen. And there are different layers in there. And the layers are here, and then they've measured some scree slopes. And so now we're starting to build this nice 3-dimensional point data set. What we can do is we can build surfaces from this. And people have been building surfaces from points for years, like a digital terrain model. That's a common example of a surface built from points. But because we have this highly detailed point cloud, we can generate more accurate representations of these different surfaces. But this has a limitation. It's very, very slow. Even robotically, it's about 1 point per second, which is very slow. But in about the mid-2000s, we started to introduce laser scanners. And a laser scanner like this one here in the left and in the image on the right, this is a terrestrial-based laser scanner where we mount the laser scanner on a tripod, like you can see in the image on the right, and we fire tens to hundreds of thousands of points at an object. This can be an outcrop. And we record all of that data. And then we've got the GPS, which tells us where we are. So we know the distance from the scanner to where the outcrop is. We also have a camera that's mounted on top of it. And the camera is mounted coaxially. So as the LiDAR scanner spins around in 360 degrees on the Z-axis, the camera takes pictures at every orientation that it spins around. And we can use that information to generate things like that photorealistic model that I showed you earlier. So if we take a laser scanner and we scan, say, a section, we generate something like this, which is what we call a point cloud, a 3-dimensional point cloud. So you might be able to pick out that there's some features in there. There's a 5-meter scale bar that gives you the scale of things. And because we've positioned it with GPS, we can know where we are in space as well. We can take that data and then we can build a surface mesh from it. And so this mesh allows us to pick out more detail. I can start to see different beds inside of it, different geological boundaries inside of it. But remember I said that there was a camera that was coaxially mounted? I can then generate a photorealistic version of that data set. So now this is exactly what I see in the field. When I was stood next to the scanner, this is what I was looking at. And so all the notes I took in my notebook, I can record those observations digitally now in a 3-dimensional model. Unfortunately, this sort of method is cost prohibitive. LiDAR kits can be upwards of over $200,000, and they really haven't come down in price. Even though this is from 2010, 2009, they're still very expensive, but they're very precise instruments. A survey grade GPS kit can be a couple of grand, up to 10 grand. But these days you can buy handheld GPS kits that collect the type of data that we need. It's accurate enough for us. That's about £500–600 or so. But it's still, I mean, that's a £600 instrument. I mean, not everyone has that type of money. Well, in the 2010s, there was another sort of revolutionary change. Drones or UAVs or UAS systems, they were more cost effective for us to purchase. So you can buy a drone for couple thousand pounds, and on the drone has a camera. And the camera, we fly around an outcrop. So the image on the right, there's a geologist up in the top left who's flying a drone, and the image on the right, part B, that shows the different positions that the geologist would fly along a cliff section. And so you take pictures at different orientations at different distances from the outcrop, because what we do is we take all of those points, or take all those images, we put them into photogrammetry software, which there are numerous types of photogrammetry software. There's expensive industrial grade, and there's even open source ones, which all do the same thing, where they will find common points of an object. So the image in the bottom left, that shows a 3D cube, and there's 3 pictures taken by a drone. The different corners of the cube have colors, and in each image, it's the same corner, so the same color. So you just find a bunch of like points, and we can recreate that 3D object, or that object into 3D. It's a very similar process with the laser scanner. So the image on the right, part C, we have different point clouds, and those point clouds we then create a mesh from, and then we put the pictures that we took with the drone on top of that mesh. We translate them around so it's an accurate pixel to point match between the pixel from the camera and the point cloud or the surface mesh. So it's a process that's been around for quite a while, but it's now much more cost effective. We can now go out and buy these drones. You can even do it with your mobile phone camera. So this is a model that I built. It's a road along not far from my house. What the people have done is they built a dry stone wall around some outcropped sections. So in the middle there, here, that's an in situ bit of rock. And on the far right, next to the scale bar, that's another in situ bit of rock. They were too big and heavy, I assume, and they just thought, let's just stick a bunch of dry stone, other blocks around it. But I built this with my mobile phone camera in open source software. I just took a bunch of pictures of this section, threw it into some software, and then I'll spit this model for me. So anyone can build a 3D model these days. But why do we care? I mean, it looks nice, right? The picture I just showed you looks really good. We can spin them around in 3D. They're nice, pretty pictures. So I was interested in how can I take this data further? How can I make it more interactive? Well, one of the things that I worked on was creating immersive environments, focus on teaching students about running around in the field, taking notes, taking measurements. So I put some of these 3D outcrop models into an Unreal Engine, which is a video game engine. And then I built an immersive environment around it. And each one of these environments you could install on anyone's machine, hit go, and then all the students could run around like they would do if they were playing a video game. They could jump up and down on top of the outcrop if they wish. They could scale the outcrop, which they normally couldn't do in person. And so this gave us another level of visualization potential, is putting these inside of 3D rendering engines. Another thing that we were working on was giving students an iPad with images on it. And these images are the images we use to build the 3D model. We would give the student the iPad, and we would say, right, while we're in the field, I want you to interpret what you see in front of the outcrop, draw it onto the iPad, and then that iPad image is sent back to a server that we had built in the laboratory. And that server will build a 3D outcrop model from the images that that student interpreted, which was really great because a student could see and compare their interpretations back in the laboratory. So student A and student B, maybe they interpreted this anticline syncline pair there differently. Maybe they took different strike and dips, but we can compare them whilst in the field, which is another step forward into bringing the field data back into the laboratory, trying to quantify the observations that we're making. Not only can we visualize this in 3D, well, we can also extract these points. So one of my colleagues, she was working on a program which allowed her to three-dimensionally extract those lines that the students will have drawn on, which is great because now we've quantified really in 3 dimensions what these interpretations are like. But I wanted to take a step further. So I jumped across the pond. I came to the University of Manchester and I was like, what's out there? What can I do? How can I work with this data better? Well, there's a lot of different types of software out there. Some industrial, some open source data that allows you to visualize and then interpret and then extract data analytics from the outcrop data. So we've come quite a long way from shooting 1 point per second to building really nice 3D models, even with your mobile phone camera. But we want to extract quantitative information because we want to try to understand what the rocks are telling us. So an example is an application of some work that I did during my PhD, where I went to a fluvial succession in the Huesca distributed fluvial system, which is in the Ebro Basin in Spain. And this is a typical outcrop of this succession. So you might be able to pick out that there's maybe some channel sandstone bodies in there. There's some mud deposits, some overbank deposits. Maybe there's a couple of splays in there. So I would go out there with my field kit. I'd have my notebook, I'd have everything else. And then I might do something like this, the image in the bottom left here. So I might draw some lines on a 2D picture and say, oh, I think these are the different surfaces, these are the different stories. I can maybe count how many of these sandstone bodies there might be. I'll also take a sedimentary log. So that path there is a sedimentary log. And whilst doing this log, I'll take some paleocurrent measurements. I might see I've got ripple cross-lamination, I'll take a paleocurrent of that data. And then we combine all this data together, we can start to understand what's happening, what's the story. But there's a problem with this. This is all 2-dimensional. But if we have a 3D outcrop model of this data, we can start to really extract the quantitative information. So this image in the bottom left is, it's a point cloud, and it's a classified point cloud, where I've classified the different facies, if it's a multi-story sandstone body or if it's a single-story sandstone body, which are formed by different geological processes. So it's really important to know what is the difference between them. And this could be applied, say, in the subsurface world, where we're trying to understand what's the distribution of these sandstone bodies through space, through time. I can also start to estimate things like width and thickness of these sandstone bodies. So rather than having one thickness measurement as I do my sedimentary log, if I've got it spatially, I can take the average thickness of this sandstone body across the whole outcrop, which is great because I can then generate maybe a median thickness, a maximum thickness, which is important to plug into further modeling software. I can also start to estimate the width. Now, if you're familiar with outcrops and you're especially familiar with fluvial systems, the width of a sandstone body that you see on the outcrop, that's the apparent width. It's not the true width, because depending on weathering processes, you're exposing different elements of the rocks, different angles of it. We can't really get the true width, but by having the paleocurrent information, I can integrate all of my field data into this outcrop model, and I can get a more accurate width of this data, which is really important, again, if we want to build some subsurface models. We can then start to build some sort of representation and try and tell the story of what's happening stratigraphically. What is the change in sandstone body width through time? If we're looking stratigraphically, what is the thickness change through time? So this is really important to start to build a nice story of what's happening in this fluvial system. And some other work that people have done is they've done that exact same thing. They've looked at some data of this same fluvial system that was published in 1991, where they looked at the percentage of sandstone of the channel bodies at each position from the apex to the distal part of the fluvial system. Some authors in 2020, 2021, they did the same thing, but they used digital outcrop data, and they followed the same approach. They estimated the width and the thickness of these bodies, and then they were able to calculate what's the percentage of it. And as you can see, the trend is roughly the same. The red line there is the more recent data. It's a bit more accurate because of the method that they use to collect the data as opposed to what they did in the early 90s. So this is just an example of the type of quantitative information that we can extract from these data. Now, importantly, outcrops will deteriorate over time, whether we have vegetation that grows over it, or if we've got people build houses on top of outcrops. These things will go away over time. However, if we build a 3D outcrop model of it, or even not build the model, just collect the data to build a model later on, we can do that very easily. So the image in the top there, that is a three-dimensional outcrop model that I built using imagery that I collected in 2007. So the very first outcrop model that I showed you that I built, that was with LiDAR. This was built with photogrammetry, but the same pictures were used. I went to this outcrop back in 2018. I couldn't get access to it. The vegetation covers up a significant amount of it, as you can see. The facilities manager wouldn't let me down onto the rocks because the vegetation had grown so thick that he didn't know what the footing was like. And there's lots of dangerous critters in this part of America, which can hide under these rocks and around these the bushes and the shrubbery. So what I did was I did an analysis of exposure level. And what we see is a 51% decrease in exposure. That's significant. That's a lot of the exposure that is not there. I can't see stories anymore. I can't measure the thickness of things. So this not only reduces what we can see, it increases the uncertainty in our interpretation of the data. If I can't see where a story contact is, I can't measure the thickness, I don't know what's happening really in space and time in this section. But because I collected data in 2007, I can go back to it. I can revisit it. I can reinterpret it. When I interpreted these rocks in 2007, I'd only taken an undergraduate course. After my PhD, I know a lot more now. I can go back to these outcrops and I can reinterpret it. And as concepts advance, I can reinterpret it again and again and again. And people beyond me, I hope they do go back and they reinterpret this data again. Another example are like an anthropogenic action. So what we're seeing here is an outcrop, and it's a key outcrop because there are some perisequence sets in there in the different banding. So there's a perisequence set here up near the top of the outcrop, near to the vegetation. So there's a perisequence set in here, and then just below that is another perisequence set. The different colored rocks tell you the different perisequences. But in just 5 years, a petrol station was built on top of this, and you let the vegetation just carry on growing. You can't visit this outcrop anymore at all. You can't even see the rocks. And this is privately owned, so you can't go digging out the vegetation either, which is what I might like to do. I can't do that. Unfortunately, I don't have any 3D outcrop data. This is from Google Earth. So I can't go back and I can't revisit it. And more of this is happening. And of course, as we expand and we have to build new infrastructure, we should capture the outcrop before it disappears. So this schematic here is just showing how much of the outcrop was gone. So in 2014, we could see almost all of that exposed. In 2021, none of it was either removed or covered. Another example of natural denudation is this, which is the largest rockfall in about 60 years that happened on the Jurassic Coast. This is a drone shot by James Loveridge, and it shows the amount of material that was removed and that flowed down the cliff section. This is the World Heritage Site. This outcrop section, if we wanted a fossil hunt, we can't go there and visit. It's too dangerous to go fossil hunt. But had we captured enough pictures and preserved it, we could go into this area and analyze the geology again. Luckily, we can do things like take pictures at different times. So the image on the bottom left there shows a repeat survey in 2017 and 2022. What we did was we did a simple difference between the 3D outcrop models, and we can start to extract volumes of material that's lost. Now, this is really important because material tends to fall if around faults or where there's weaknesses in the bedding and in the rock. This can help us determine where our weaknesses are that we may not be able to see if we just look at it in 2017, separately from 2022. But because we have imagery, temporal imagery, we can start to analyze these sorts of things. And perhaps what's most important is 3D outcrops permit accessibility. That outcrop I showed in the very beginning, that's in the middle of Arkansas. You can't access it because there's vegetation growth, but if you don't know where it is in Arkansas, or you don't know a person who knows where it is, or you don't visit America, you can't visit that outcrop. And it's really amazing outcrop to show the fluvial succession, but we can't visit it. So here in the UK, I can now go back to Arkansas whenever I want to. So people who may not be able to access these outcrops for a myriad of reasons, they now can, because we have a digital recording of this data. It also permits reproducibility, which, as we all know as scientists, is key. We need to be able to reproduce our results. We need to run an experiment, reproduce our results. Having an outcrop allows us to do that. There are several initiatives around the world where they store some of these 3D outcrop models. So in the image on the right there, this is Hutton's Unconformity near Sticker Point. This model is hosted on eRock, which is free and accessible for anyone. There's a QR code that you can see in the top left. I'll have a bigger version of the QR code later in the talk. And if you want to take a picture of it, you can visit the outcrop. That QR code will take you right to the outcrop. So wherever you sat around the world or here in the audience, you can go to Hutton's Unconformity and you can look at Sticker Point just on your mobile phone or any mobile device. We've probably all heard of virtual field trips. These are not new. They've been around for a while. A version of this is the outcrop that I put inside of the Unreal Engine. That was essentially a virtual field trip. I gave students the outcrops, a bit of the geologic history, and I said, great, I'm going to take you around and show you these different outcrops. But because it's a lot easier to build 3D models now, we can fly a drone and we can take pictures with our phone. We can start to design virtual field trips of our own, whether it's your local geological society or it's the geological society, or if it's a much larger organization. You can have lots of virtual field trips to these key outcrops. It's really important for education because students who may not be able to access these areas, they can. And what we like to do is students make qualitative observations because it's on a screen in front of them, or they might take some measurements depending on the software they have, but we can quantify those observations. So we can find out what's good and what's bad about the different virtual field trips. Are we showing the right information? Are they able to understand the geological principles that we're trying to teach? So what this does, allows us to create better virtual field trips. It allows us to generate exercises for students before they go out, teach them a bit of the geology, maybe show them the model beforehand, go out with them into the field, give them some of the books that we would normally take out in the field, some printed off some notebooks on a binder, but send it to them as a PDF, and they'll have it in front of them at the same time that they're looking at the 3D model, just like we would in the field. We give them a binder with some pages, and they can hold it up and they can look at the cliff section in the field. Well, we can do the exact same thing here. But crucially, we can integrate data that we've collected in the field. So we've got sedimentary logs, for example. We've taken samples like they've shown here, where we've got geochemical analysis or we've got gamma ray readings. We can digitally and we can actively show them what it's like. And geology it's a science of telling stories, right? We're trying to tell the story of deposition or of structural history of some area. This is a great way for us to tell a story because we can take them through step by step how this thing came about. And if in the field, if we had moved on and driven down the valley, we can't go back very easily if a student maybe didn't understand it. But because we have it all virtually, we can take the student right back to the same area and explain these concepts to them. Unfortunately, in 2020, there was a global pandemic, forced everyone to be locked inside of their homes. This was not good for field geology. We couldn't take students into the field anymore. We couldn't teach them the key skills that we need to teach them: spatial reasoning, temporal reasoning, and understanding. Well, luckily, a lot of people, including myself, have been collecting 3D outcrop data for a long time, nearly 20 years, just over 15 years. We have data, so we can now take students into the field virtually, which was a really great thing from 2020 to into 2022. Because if students couldn't fly to an area, or we couldn't drive because we couldn't be in close proximity, we can all hang out on the same outcrop virtually. So after that, we've seen 3D outcrops rise significantly in use. We've seen them show up as kind of like here, we've got people that are attending virtually. They couldn't be here in person, or they can hang out online. The same thing when you have a virtual field trip. To wrap it up, our mapping methods haven't really changed in 200 years. We still go out there. I still go out with a notebook, a map, some colored pencils, compass clinometer. But at the same time, I have my mobile phone with me, so I can take pictures of this outcrop that I'm making observations of. I can digitally record these observations and put them into the model, so that a log that I take up an outcrop, I can record that log digitally. Now I've got a digital record of that. As Reid said, the best geologist is the one who has seen the most rocks. Well, how true is that? Well, I think it's very true with the digital outcrops, because there are rocks that everyone can see now. We can, through some of these online databases, we can take people to different areas around the world and we can show them more rocks. So the more rocks you see, the better you become, because you can recognize different things. 3D outcrops, I mean, they have a relatively short history, about 20 years or so, but because technology is advanced such that we can collect data easily and we can process it using things like open source software, anyone can build an outcrop model. So we've seen a significant number of outcrop models appearing in the wild, which is really, really great to see. Outcrops do deteriorate over time, as I've said, whether it be vegetation growth, erosion, but alarmingly, anthropogenic actions do outpace this amount of denudation. So the petrol station that was built on top of that outcrop, that's happening everywhere. But if we have an outcrop model, we preserve that. Outcrop models are an inherent archive of the data. What they do is, at the time of their collection interpretation, they preserve the current thinking of that interpretation. 20 years from now, 25 years from now, I hope we've come up with better methods, and we will come up with better methods. And then we can go back and we can reinterpret them again. But it's really great that we have this archive of the interpretation of the data at that time. So I'll just end it there and say, so the time has never been more appropriate, and we have tools that are accessible, your mobile phone, for example, where we can preserve the outcrops around us. This in turn facilitates greater accessibility, inclusivity, and then fundamentally reproducibility of geology. A list of references of everyone, all the papers cited, and then I'll leave it there with a special thanks to the Geological Society for inviting me down to give this talk, and to the late Carlos Aiken and David Hodgetts for pushing me to think outside the box. What else can we do? All of my co-authors, both at the University of Texas, Aberdeen, Manchester, and around the world, and Total is thanked for supporting my PhD. And as promised, that is the QR code that you can take a picture of. You can look at it through your phone, and it will take you to Hutton's Unconformity. Thank you very much.
Hopefully this is going to come on. Hello? There we go. So I'm going to take chair's privilege and ask the first question, if that's okay, to give Alicia time to grab a mic and start running around.
Great, yeah.
So all of this is absolutely fantastic, and we're seeing this a lot in education settings, and the stuff that we can do in the field and actually sort of ground truth ourselves, being out there in the field, those of us that can get there, to creating these digital models is one thing. I'm a planetary geoscientist, so I don't get to go to my field area very often.
Yeah.
Has anyone used the same skills and techniques that you're using with the data that rovers are collecting and satellites to see how comparable it is when we can't physically get to the field?
Yes, a lot of people are using like high-res imagery, for example, and the rovers building three-dimensional models and then running virtual field trips around it. I mean, you can build a 3D model and you can track the rover on Mars, for example, and you can pull the pictures down, build a 3D model, and you can make interpretations. Any of the software that I showed previously, you can interpret some of these 3D models created from these images. There are people that are doing it. I haven't done it. I'd love to go do some planetary geology, but I do know of people that are doing that.
Fantastic. Good to hear. Okay, over to you, Alicia.
We have a question from Steve Peacock. He says, even with great 3D models of inaccessible outcrops at some stage, sampling would obviously be critical to ground truth interpretations. Are you also working on or linking with innovative ways of remote sampling, for example, taking cores via drones or other wacky ideas?
I would love to fly a drone up onto a cliff and take a core sample. But you're right, it's fundamental to integrate hand on the outcrop observations so that we can integrate that data with the 3D outcrops. The time isn't there yet, I don't think, to take cores, but there are people who will fly a drone around an active volcano. You guys may have seen this with a heat sensor on the drone, and so they can map the heat flow properties as the volcano is erupting and before it erupts.
Thank you. We also have another one online from Graham Mayo. He asks, do you use VR headsets? And if so, does this add to the experience?
I do use VR headsets. It does add to the experience because the image that you see on here, this is part of that fluvial succession in Spain. And I can spin this around, but this is just a 2D image in front of me, but I can spin it around in 3D space. But having a VR headset adds a whole nother level of interactivity and immersion to this, which you're on the outcrop in VR. You can make interpretations in VR. The software that I'm working on allows you to do that. Virtual Reality Geological Studio, we have VR headsets and we've got basic interpretation tools, which is really great because we can run virtual field trips in VR, which some people can take to VR, some people don't. It can make you a bit motion sickness if you're that way inclined, but it really does add to the immersion of it.
Are there any questions from anyone in the room before we go back to online? Not just yet.
So Gary Robertson has asked, in your experience, are there any aspects of in-person fieldwork that are lost with 3D digital fieldwork?
Great question. I would say yes. There's a certain level of camaraderie, I guess is a word for it, when you're in the field with either your field assistant or with a bunch of students. Like when I was a student, it was great to go out in the field. We did lots of camping, so there was a bonding activity. We all sort of hung out together, interpreted the rocks together. So you do lose that aspect of it, of building those sort of personal relationships in the field. You can't put your hand on the outcrop, so I can't feel the grain size difference. I can make a measurement and went with scale if I want to, but you lose that tactility. However, I think we gain a lot by having a 3D outcrop because we can revisit an outcrop, for example. I can access a cliff, but I wouldn't even be able to get up to it all and make the measurements that I need to make.
Great, thanks. We've had quite a few questions regarding how to build 3D models using your phone, as expected. So how do you build 3D models using your phone? And second part of the question, what is the name of an open source 3D model building software that you can use with your phone?
Right. So to build a 3D model with your phone, you follow photogrammetry principles, which simply is take lots of pictures at different angles of the feature that you want to build a 3D model of. And make sure that the images, there's about 60% overlap between the images as you move along. I tend to go from right to left or left to right, and then just take lots of pictures below, in the middle, above. Make sure there's 60% overlap because you want to capture the cool stuff that you want to see. And the free software out there. So the model that I showed of the dry stone wall that were built around the outcrops, I use something called Meshroom, Alice Vision Meshroom, which is very easy to use. You put your pictures in and it's got little boxes that tell you step by step how to build your 3D model. And then out spits a nice, lovely 3D model. So that's what I would recommend that you go for. There's other open source software solutions out there, but that's the one that I tend to use.
I have a quick follow-up to that, if it's okay. It was something you mentioned earlier in the talk and that answer. So obviously phones are getting really sophisticated now, and it's really easy with the open source software you've just described to be able to build the photogrammetry models.
Yeah.
Have you used any of these? People that have higher end smartphones than I do have inbuilt LiDAR scanners now. Have you used the techniques that you were describing in your PhD with the super expensive LiDAR DSLR combination with a phone LiDAR and phone camera combination to see what it looks like?
Great question. I haven't. I've been on the Android train from the beginning. And yeah, and Android don't have that capability. But I have seen really great 3D models built from LiDAR. I know there's people who will build a model if they're walking along some sort of nature trail. They'll build a 3D model of an outcrop that they see, which is great, which everyone should do. And then there are people that work, say, in flume tanks. They'll build a 3D model of after wave propagation, and they want to monitor the bed morphology. They'll build a 3D model with their phone LiDAR, and then so you can start to build temporally, what does that look like in 3 dimensions? So I haven't. I plan to experiment with it, so stay tuned. There'll be something coming up soon where I'll mention it, but I haven't. I want one of those phones, but I don't want to commit out of Android.
Have to be able to borrow an iPad off someone or
That's
something.
it. Yeah, exactly.
Any questions in the room before we go back to Alicia? I'm just going to, okay, one at the back and then we'll come to the one at the front.
Hi. I was thinking that when you have a plain area, sometimes we use DGPS for georeferencing the images.
Yeah.
Now, when you see these kind of remote areas where you just don't go and you capture the imageries, like how do you then georeference those images so that you can actually get the proper measurement of the entire outcrop?
Do you mean with LiDAR or with photogrammetry?
Yeah.
Or either?
I was saying about like people are using real-time kinematics drones.
Yeah.
Like when, because if you just capture the images by simple drone, they have some kind of errors. So when by
yeah.
using simple images, if you are creating this outcrop and doing any measurement, this may not be very precise.
You're right. Yeah.
1 centimeter could be like 1 point something like that.
Yeah. So we always georeference everything, usually with a differential grade GPS. So for this example, this outcrop here, I had GPS points that I had captured on the top of that cliff there and then along the bottom. So when I built the 3D model, I just typed in the tie points of that position in space, and then the model was scaled accurately to that.
Okay.
So you can do the same thing if you build a 3D model and then you've got a cliff section that's say 100 meters away. If you've got GPS points around you that you've collected and they're all within that same, in the images, in the 3D model that you built, it's all georeferenced accurately.
Okay. Thank you.
Yeah, thanks a lot. I recently enjoyed reading the Mary Annan book of discoveries on the Jurassic coast. So your image of the landslide came home to me pretty quickly. And you said it's not permitted to climb that landslide because of the lack of safety, the personal risk. So if you flew your drone instruments over the landslip itself, the recent landslip, do you reckon you could identify, do you have the resolution to highlight outcropping newly exposed plesiosaur?
Wow, well, good question.
Great question.
Yes, if it's exposed, if that cliff collapse has exposed it, yeah, you could definitely, depending on how close you got to it and the resolution of the picture, yeah, you could. And then of course you'd have to get health and safety on board to make sure you don't cause any more collapse. But if we fly the drone over that recent cliff collapse, we can also start to look at geotechnics of the area. So we can start to map faults that may have formed or areas which would be at risk of other slippage.
Great question. Sounds like a good funding application to us in the future to support some research in that.
Intent.
Alicia, back to you.
So we have a question from Brent Wilson. He asks, are there any indications that there may be made compulsory for such data to be collected prior to a development in the way that, say, our fellow archaeologists are able to undertake a dig at a site?
I hope so. Currently there's not, but I certainly think so. So the outcrop that I showed of the fluvial section in Arkansas that you can't visit anymore because there's vegetation growth, a lot of students went there. When I visited there as an undergraduate, there was another university set of students there because it was such a great locality to look at really basic sedimentary principles. We can't go there anymore. Even people in the energy industry went there. We can't go there anymore. So I think it should absolutely be compulsory to preserve these outcrops, especially sort of key outcrops. So Hudson's Unconformity, it's on the coast. I mean, eventually it'll take a long time, but that will collapse at some point. But we have a 3D model of it now, which is great. We can go back to these type of localities. So the GelSox 100 geosites, we should absolutely go out and build some models of that.
So we have another question from Serini. Many thanks for the great lecture. Is there a way to engage school students, for example, those studying geography at GCSE or A-level, by a body that can provide minimal training and get them involved and focused in mapping? This is with a view to broad-based contributions from non-geologists.
Oh, yes, I like that idea, sending a representative around to yeah, no, I like that. I think it'd be pretty easy because there's open source software. We can build 3D models and we can build models of local geology around the area. I mean, the same principle can be applied to geography. If you want to look at terrain, geomorphology, you just fly a drone and you take a bunch of pictures and then you can build some sort of geomorphological map of the area and then show students that quite easily inside of some of the free visualization software that's out there. And take them on virtual field trips, show them some of the cool stuff in the area. I think there should absolutely be one. That sounds like something that I should talk to someone else about later.
Is there a final question online, Alicia?
Yep, unfortunately, we won't have time to answer all your questions that you've posted online. So Adriana asks, I understand that the technology you showed is well orientated towards education. What other uses could it have, for example, in mining?
Ah, yes, great question. So photogrammetry are pictures. Pictures rely on light right? Light on reflection of the light from the outcrop to then take that nice pretty picture. In mining, I would suggest something like LiDAR, because you can take it into the mine and it doesn't need light because it uses near infrared lasers. So you can build a 3D map of what your mine looks like. You can map things like fractures, for example, map where places of instability might be using that three-dimensional data. But if you've got a flash enabled on that camera, you can take flash pictures of the mine, for example, and so then you have some sort of photorealistic version of it, but the really precise LiDAR will really help you in things like mines.
Thank you.
Cool. Well, thank you very much. And I'm really sorry to those of you online with such a large audience online. I think we were always risking not getting through all of the questions. But thank you so much for being engaged, both those of you in the room and online. And I hope you'll all join me in thanking Brian again for this evening's talk. Thank you.
Thank you.
Cool. Well, just to remind those of you online, as you're leaving, that please keep an eye out on our website for upcoming public lectures and events that are available through the Geological Society. And we look forward to welcoming you back soon. Thank you.
I've done a lot of exploration in Japan. Japan, they're massive road builders.